Cool. Okay. So thank you for having me. Thank you, everyone attending. I hope we will have a good time. As said, if you have questions, just throw in the chat. We try to go through them right away because this is a demo-driven session, so it makes sense to try to answer your questions while we are there. But if not, in the end, we'll get still a couple of minutes to go through if needed. Welcome to let me show you why the data types still matter. My name is Cláudio Silva and my pronouns are he, him. I work for Data Masterminds. Mainly my day-to-day work is inside of a management studio, working with performance tuning on T-SQL. And when I'm not doing that, I'm doing some automation with PowerShell. And I'm a proud contributor for the DBA Tools and DBA Checks open source projects. And as you see on the right, I have also been co-author on the Learn DBA Tools in the month of lunch. And below here, you will have all my contacts, being the more important ones, I would say, LinkedIn, the website, and my GitHub, to where you can then also find today's session and demos. So enough of slides. We want to see demos. Let's see what we have for today. So data types is something that people often overlook, and until we get to a bigger database size, more records on specific tables and so on, it seems that it's not a problem. Nothing happens, nothing is broken, so we can just select whatever data types we want. I will try to show a bunch of real situations that I saw before, where these assumptions can be quite easy problematic. For today, my environment, I'm using a SQL Server 2022 on a container. Okay, so as you may see here, a little penguin here, and I generated just an empty database, and I will run the demos on top of that database. So if you want to work by yourself later, you can grab the code, you can create a database, and you can go through each demo to understand something that maybe you miss it, or to test a slightly different approach. So first demo. Let's start talking about string concatenation. So in this case, for this demo, I'm not even using any tables itself. The idea is just to show what happens when we combine strings with different data types. And in this case, I'm talking about being or not being a Unicode. And also the size of this data type. So whenever we use the max, or for instance, whenever we use a different value. And to show this, I'm using the replicate function, which in the end accepts one parameter, and it will replicate that parameter X amount of times. And I'm concatenating that with another replicate for a different letter and a different value. So to start with the known Unicode, the first thing to talk about that is the main difference between the NVARCHAR or the VARCHAR is the size that it occupies. So with the known Unicode, one character occupies 1 byte. With the Unicode, with the one that has the N something, occupies 2 bytes. Okay. So here, if I have a variable with a varchar max, which means that I can have up to 2 gigabytes of data inside of this variable, what do you think it will be the output of this len? So I'm trying to get the length of the string when I concatenate 7,500 records plus 510. So out of the box, everyone will be expecting to get 8,000 and 10. However, we don't get more than 8,000. Okay. Why this happens? So the main reason in this specific case is that the replicate function will output the same data type from the input. And as you can see here, I'm doing an input of A not being Unicode, being just, or is not Unicode, but I'm also not saying that this A should be a varchar max, meaning that in the end, the max of this value will be 8,000 characters, okay? And therefore, if I do the concatenation of both, even that my variable is a varchar max, because these ones won't be varchar max, it will be cut on the 8,000, okay? So that means that if I replicate here Unicode, so I'm using the n before the string with a known Unicode, then probably it will be okay, right? Well, it won't. And to be fair, in this case, we have even less than the 8,000. We start having just 4,000. Why? Because the max size of an NVARCHAR column without the max will be 4,000. And here, as said before, will happen the same thing. So the output of these results will be just 4,000 because this is just a Unicode. And then when concatenate with the other one, well, in this case, doesn't matter because we already fulfilled the 4,000 being from here, okay? So that is the reason why in this specific case, it won't bring more than 4,000. Okay, so to fix this, we can do something like this. We can cast our input parameter as being of the type NVARCHAR max, and therefore, when we concatenate with something else, our main and the first input is already NVARCHAR max. Then when we append the 510, we end having the 8,010. Okay, so in this case, the main point is that if you want to have a varchar max because you are expecting to have either more than 4,000 or more than 8,000 characters, you should cast and you should enforce that you have the proper data type and the proper data size. Then here, I just want to show that that here everything should be fine because we are concatenating this NVARCHAR max with 7,500. And if I use another one to concatenate the 810, see that the outcome of this, instead of being 15,510, is only 11,500. Why? Because this replicate thing again can only have up to 8,000, so the 10 characters here will be just cut off from and truncated from that string. Finally, just to show that how you can double check how much a variable in this case is occupying in terms of length, in terms of bytes. For that, you should use the data length function. And here, as said before, because we are using a variable that is non-Unicode, one byte will be one character will be 1 byte, and therefore, if I have 1,500, I will have 1,500 bytes in this case. So the story, the real story I had with this, a client that was doing some concatenation between some text and some table column, and all of a sudden something's broke and stopped working. And they said, well, we didn't change the process, and that is okay. The problem is that the data that was on that table, because it's dynamic and the column that appears inside can be bigger or smaller, they reach this kind of fence between having a varchar max or not max and having a Unicode and not Unicode. Turns out they were concatenating constant strings that some were NVARCHAR, some were just varchar, and together with that value from the column, when everything was concatenated, it surpassed the 8,000 characters. And when they tried to run that SQL, dynamic SQL, it failed, saying that the T-SQL was not valid. Down here, you can then run, but this is the same examples, but with the N varchar, all these outputs will be the same. I just want to show the final one, which is the one that shows that for NVARCHAR, in this case, we will get the double of the bytes. So instead of having just the 15,000, we have 31,000 in this case, because each character will occupy 2 bytes. Okay. Takeaways: be aware of truncations, be aware of having string concatenations and the data types that each string has, because it's quite easy that we just append some plus sign to do something else, and then the variable that where you are putting those results needs to be big enough. And try always to keep the same data type, in this case, either just Unicode or non-Unicode, so you make sure that you don't get lost on conversions in this case. Any questions on this one? If not, I'm going to move to the second one.
There currently are no questions.
Thank you. All right, second one, float data types. So a float data type, as it says on the top, and that is copied from the documentation, it's an approximate number, not an exact number, meaning that the values can float around and they will not be precise. How can we kind of prove that and check that? So let's start with this execution here. What I'm doing here, I'm declaring 2 variables that are from the float data type. I'm saying that is 0.1 and this is 0.2, and I'm doing an addition of both. So I'm summing those values, and here, picking on that sum, I'm asking if that will be equal to 0.3. So first question, if you give them a thumbs up, if 0.1 plus 0.2 is a 0.3 or not. Because for me, it is. For the computers, not really. So what's happening here? Is SQL Server having a bad day today? Is this something known? Why I have a 0.3 here, but when I'm doing the comparison here to say it's true, after all, I'm getting the false. Interesting. So let's see. The first thing here is to say that this situation of the 0.3 here is Management Studio, the SSMS problem, let's say this way. So this is a known thing, but the problem is this 0.3 is from the SSMS problem. So let me show you if I go to Azure Data Studio, and if I run the same instruction, look what is the output. Is 0.3, 15 zeros, 4. So it's not just 0.3, and therefore SQL Server is correct, it's false, because 0.30004 is not the same thing as 0.3, right? So in this case, SSMS is showing us a cut version of that, okay? So that is something to keep in mind. Back to the SSMS, let me just also bring here one other example, which is using the SQL CMD utility, and running the same thing on my database. You can also see that the output of this is the 0.3, 15 zeros, 4. Okay, so only Management Studio is lying to us. But I don't know, I normally live inside of the SSMS, and I'm relying on that. So it's important to understand these situations with faults. So let's see now what happens with equality. We kind of already saw, right? Because if we are doing a sum between 0.1 and 0.2, and the results are stored on the database is 0.30004, it's not exactly what I was expecting. So just to say that, first of all, the default data type for SQL Server can represent between, so the precision can be between 1 and 53. That is called the mantissa of the data type. However, SQL Server just either saves it as 24 or as a 53. And if you declare a float without any precision, like this one here, by default, this will be the 53, okay? So if I create here a table with different float values, and if I insert just one record on the column float, and I'm doing the 0.1 plus the 0.2, one record is inserted. If I select the data now, not from the variable, not from that select between the variables, but from a table, we can still see 0.3. But now this is where the problems will start. So if I see 0.3 and I imagine I have a million records here and I want to filter out by the 0.3, I will run a query like this. And then I have no results. Okay. But maybe SQL Server is having a bad day and I really need to put the 0 here. Doesn't make any difference, of course. Or even let me declare a variable being from the same data type and saying that this is 0.3 because that's what I saw from SSMS. And if I do the filter, still nothing. What about if I use a different precision? So let me try with a different one. Still nothing. So nothing appears here. What about I do the filter based on the value that either SQL CMD and Azure Data Studio are showing to me? Boom, it works. Okay, so behind the scenes on the storage and Azure Data Studio and the SQL CMD show that the data is saved as being this value, because again, this is not a precise data type. But the SSMS is kind of doing some truncate on this number, which lead us to wrong outputs, wrong values in the end. Just another example here. If I run a while cycle that goes to iterate a plus 0.1 on a top of 4.7, and I say that I want to stop my cycle either when I reach the number 5 or until I reach something bigger than 5.2, let's see what happens. So I have print here the results. I have 4.7, 4.8, 4.9, 5, but it didn't bail out. It's still here. So I said if it is equal to 5, just go out, or until it's different to 5. But here it didn't bail out. And now we have 5.1, 5.2, and finally it bailed out. What can we see here? Here we can see that the 4.7 as a float for SQL Server and for computers in general, is not for SQL Server only, is 4.69 something, and 4.8. And when we reach the 5, which was our condition to stop the cycle, to be fair, was 4.99, and so on and so on until we get to something bigger than 5.2, and therefore we bail out. So another quick thing to remember here is that depending on the precision that you are using, so if either is 52, if it is 1, you can see quite different numbers because of the truncation of this number. And that also is something to keep in mind, that when we cross the boundary between the 24 to the 25, or when we have the 53, what happens is that now we are taking, instead of 4 bytes until we get to the 24, and we start having 8 bytes when we reach the 25, the other one. So the precision change. Now, real story, a client using floats to do some calculations. I will not say that had some money involved, and using the ceiling function. Ceiling function is a function that if you have a number, it will round to the next integer, let's say. So if I have 0.7 here, the ceiling will be 1. If I have 1.001, which is already higher than 1, the ceiling will return 2. Okay. So what happens when we are using this with our floats? what happens is that if, let's see, case by case, here I have a fault 0.1, which is this one here. But to be fair, if I cast as a fault with more precision, is 0.1 something, 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 and a bigger number. And the same thing with the 0.2, which is this one here. So next, the question is, what happens if I'm doing some math between them? Again, I'm summing 0.1, I'm summing 0.2 and 0.7. So we would expect to be just 1. However, the sum is 1 point something, right? The same thing, even if I cast my 0.7 as a float, and even if I cast with 0.24, so with less precision, being that one, also interesting because instead of being 1 point something, is still 0 point something. So when we're using the ceiling on top of these sums that we are doing, we will get results like this. It's bigger than 1, we get a ceiling of 2. The same one from here, but then in this example is a little bit before 1, so the ceiling will be 1. So now which one is the correct result for you? Is these 2 values or this 1 value, right? So be aware when working with faults if that is really what you need, depending on what you are trying to achieve. Maybe the fault is not the right data type that you are expecting, okay? You may ask, okay, but if I really want to have fault and I really want to format the entire number and output that entire number, how can I do it? You can use the str function. As you can see here, it will output with the bigger precision, even that the SSMS by default would just cut it out, okay? A couple of takeaways. If you don't, if you want to use fault, make sure that you use for things you can measure, but you don't need a lot of precision because, as you are seeing, there is always a slight deviation. Avoid using faults if the accuracy is important, of course. As we saw, using equality and inequality checks will probably put you in trouble. Rounding numbers and things that you can't avoid fault. If you still want to use something with the decimal part, I suggest that you use the decimal instead, and you can have a precision up to 38. Also, if you want to play around with these numbers and how it works, there is also here some links with some online converters / calculators that you can see, depending on the mantisa that you have, what is the actual number in a decimal way, so therefore what is stored in the storage. And also, to understand better why the 3, 15 zeros, 4, there are a couple of websites that also shows and explain to you how that works. And again, this is cross-language. This is not a SQL Server situation or a SQL Server problem. There is also some image or some meme talking about this. Oh, yeah, our Java guys went 1 day to understand what was the problem, and the problem was the floating point. So that is the takeaways for the fault. Any questions here? I see none.
No questions at this point in time.
Cool. Next one. Let's talk about implicit conversion. So we have talked about concatenated strings, doing some operations and working with some numbers. Now let's bring also some other tables into play and check how the right or wrong data types can hurt us in terms of performance in some situations. I'm creating here a table called implicit transactions and heading 1 million records. I will create an index. So I already have the primary key, but I'm also creating a non-clustered index on the column name. Now I will pick one of these results to put it here in my queries, and I will run these queries after I turn on my execution plan and the statistics times IO. Okay, so pretty much the same execution plan, it seems, until we start looking to a couple of tips that SSMS is giving to us. Being the first one, this yellow triangle here. So we see the L triangle saying that we have a warning, which in this case is actually two warnings, but let's just focus on the first one, saying that SQL Server had to do an implicit conversion of the column name to a NVARCHAR 8 to be able to do the comparison with the variable name. Okay? And the second one is about the memory grant, that it says it needs 1 megabyte memory grant, and then that was too much because it used 0. Okay? On the second one, we don't have any of those. Okay. What else is different? It's different that the first execution did an index scan. An index scan can be either a scan of the entire index or just a range scan, a portion of the index. But still, it seems that it did a little bit more work than needed because the second one did an index seek, because we are searching for a specific value. Those values in this case do not duplicate, that do not have duplicates, so it's just to get one record. Also, we can see here that the execution time for this operator compared with this one is like 167 times slower, this one here, right? Well, how can we also check that? Here with the statistics time and IO, we can see that our first query did one scan count, but did more than 2,700 logical reads. However, the same query with a slightly different approach, or in this case, just the variable that we are using as being the name being slightly different, just did 6. And that's why we have 170 milliseconds elapsed time versus 0 from the second one. So the main difference in this case is about this Unicode and the non-Unicode here. So the column is non-Unicode, and that's why having the varchar made it possible to use a seek. Whenever we said to use a non-Unicode, because I just looked at the table and the column name is a name, I thought, okay, let's make it the Unicode one. Then this value makes the engine to say, okay, if you want to compare to a Unicode, but on my table I have a known Unicode, I will need to convert, because of the precedence of the data types, I need to convert everything as being Unicode to then being able to do my check and my filter, okay? Let me show you, because this is like 170 something bytes, right? Sorry, milliseconds, meaning that that's, I mean, if you run that query once in a while, that is won't be a huge deal. However, what I want to show you is what can happen if I say to run 400 times the same query, how much time it takes one version versus the other. Okay, so this is the SQL Query Stress tool. You can throw here some queries, you connect to a database, you can say how many threads you want. I'm saying 8. I can also say how many iterations I want that each thread do the call of this query. And when I hit go, I have 400 executions in 15 seconds. If I do the same thing with the known Unicode one, which is the proper data type in this case for my database, this is the difference. Which one do you prefer? 15 seconds for 400 executions or less than 1 second for the same 400 executions? So when someone says, oh, that doesn't matter because it's only 100 milliseconds or whatever, yeah, sure, until a couple of months that your application is growing, you have more data on your tables are bigger, and whenever you need to do these implicit conversions, you will need to convert each day more and more records to fulfill your query. And by having the same or the correct data types, in this case, just on the variable side, can make your query goes like 15 times faster on the same number of executions. Next, what about numbers? So I have a column called codes, and because it's called code, I thought, because I can think about that, it is a number, okay? Problem is not, is a string, because someone decided to be a string, which is okay. So the thinking again here is to say, double check your data types, double check the query that you are running against which objects, what are the data types that you have there, especially when declaring variables, doing filtering, because you want to be able to match the same data type. What happens in this case is that just to do a select star, again, I can use a cluster index here without having any yellow triangle, meaning that doesn't have any conversion of the data type. And in this one, I have the conversion, so it's slightly slower. But more than that, what about if I create an index on that column? Because then I can use just the index. Yeah, that is correct. And we can see if I'm selecting just the ID of the table, which is part of the cluster index, I can get results, and it takes the index scan, so the non-cluster index scan, and it took 100 milliseconds. But when using the proper data type, in this case being a string, we can see that it takes 0, okay, seconds to or milliseconds to run, and we have the in this case the same output. But now, one other thing to be aware, and you can check this thing about the precedence data types to check which ones will need to be converted before being compared in each situation. Still on the data types, what happens if I'm doing inequalities? If I'm saying I want everything that is bigger than the 661, but this 661 number or 661 string? Because that is completely different in terms of results. I can have here 100,000 records or 600,000. Okay, so be aware again, if you assume the data types and you don't double check them, you can end having these kind of situations. Just to give an example, in this case, if I want to deal to order by and get the data being a code int, I can force the order by as being a hint data type. And what you see here is that if I don't force that, I have a string order by. So after the 10, I have 100, and after that, 1000. If I say that I want to order by a code being an integer, then I have 2, 3, 4, and whatever else. Okay, so again, don't do assumptions regarding data types, double check them, avoid implicit conversions, because that can hit very hard on your systems, even more on queries that runs a lot. Okay, next one.
Claudio, we have a question coming in.
Yes.
So how would you detect data types mismatches? Is there a better way than to explore the query plans?
So query plans is one way to see it live, let's say, or the compiled plan can also show you these situations. Another way will be querying your plan cache to find on the XML text that the plan has, where you find the implicit conversions. There is, to be fair, one other way to do that, but only works on 2022 for now, because it's an extended event that can create an event and find some anti-patterns. And one of those anti-patterns showed there is the implicit conversions. So if you have that query, that extended event running, and you have your normal work code going in, and after a couple of minutes, if you go to your extended event, if you find entries about implicit conversions, it will tell you which query was getting that. In the end of the session, if you remind me or if you drop me a message, I can send you one example and the link where you can find that. But if you try to find by extended events anti-patterns, there is a new one for 2022 that works that way. Unfortunately, won't be able to work with 19 and previous versions, but at least it's a start somehow. All right, next example. Let's talk about partition elimination. Is anyone not aware what partition elimination stands for? What is useful for? So partition elimination is the ability. So first of all, sorry, let me do a disclaimer. Partitioning is not a performance feature, okay? Partitioning is a feature that normally we use with bigger tables that we want later to housekeeping and to move partitions to some tombstone or to truncate those old partitions. And by having the partitioning in place, we can have some metadata operations, which instead of doing the data movement, they just do some pointers to the different table, and that make the operations much faster and less blocking, less intrusive on your system, and so on. However, when you have partitioning in place, if you do the queries in a proper way, and if you can, and if you are filtering by the column that is part of the partition key, you can get something called partition elimination, which is the ability of the engine to discard to read some partitions because it will already know that the value that you are trying to find won't appear there. Let's see what an example. So I created one partition table and one non-partitioning table. This table is partitioned on some IDs, some numbers. And I inserted a bunch of records. I duplicate or copy those records to the non-partition table so we have the same data, the same values. And here I'm just showing that I have here the partition number where these columns or these records are appearing. And you can see here something 1, 2, and 4 and 5 on this column. So we have a bunch of data on a couple of partitions. So now, what happens if I run and say that I want to go to my table that is actually partitioned and I want to search for data that are bigger or where the column 1 is bigger than 1500? So I get the data. I see here that I did one scan count with 145 logical reads. And the important part to be able to read this thing is about these two things here. The first one that says, yes, this table is partitioned. And the second one says, well, the actual partition count, this means the amount of partitions that I read was just 1. But I have 5 or 6 partitions on this table, okay? So what happens if I say that is bigger or equal? And if I say it's bigger or equal, now I get 2 scan counts and I had like extra 3 or so logical reads. And here I can now see that I have the actual partition count being 2, meaning that I touched on 2 partitions to be able to read this data. Also, if you do properties here, you can have a little bit more information saying that, yes, I read 2 partitions, and those partitions were the number 4 and number 5. Okay, so this can also help you to understand what is being touched by SQL Server for this situation. If I do this same query on a non-partitioning table, I have no information about the partitioning at all, so that attributes won't appear here saying it's partitioned or that I read because the table is not seen as having partitioning. And once again, what happens when I read bigger or equal to a value? So we already saw before that he did 2 scan counts by 5, 148, 156. These numbers changed. What's happening here? Oh, wait. So now I'm reading 5 partitions, not just 2. Don't believe me? Let me pull this one, and it says I'm reading 1 through 5. What happened? What changed? What was the problem after all? So isn't this one equal to this one? Well, maybe not. Maybe this one is an integer and this one is a big int. What happens? SQL Server cannot safely say, I just don't need to read partition 4 and 5 because I know which value are you trying to read and I know where that starts on my table, okay? So, and because that doesn't happen, or can't happen because of the data type, there is no implicit conversion exactly in this case, but the engine needs to go through the entire table to decide if there are or not data there. So if you pick your right data type from your table, and let me show here that the table was an integer, okay, here, that will help you to achieve the partition elimination whenever possible, okay? So I think that is important to understand. And why? I know, because in my database, normally we work with big ints, and by default, my memory muscle is typing big ints, but all of a sudden we have this behavior, and I'm reading 5 partitions instead of reading just 2, and making a quicker execution of the query. However, as partitioning is more related, I would say, with dates, because normally when you have data warehouses and reporting tables and stuff like that, you want to aggregate or put that data partitioned by day or month or even year. Just another example in this case. So if in this case, I will be creating a partition table with a couple more partitions in this case, each one will hold a year of data. I'm partitioning this one on my column event date time, and I'm inserting I think a couple of million records, and we need a couple more seconds to finish, and then I will show you that we can see different partitions on our data. So this dollar partition in the end is a built-in function from SQL Server, so that you can use this one together with your partition function and pass the column that does the partition, and that will tell you on which partition there is your, do you have your record. And now it's taking a little bit longer than I would expect. Because it's already outputting the results, sure. So here you can see 4 and 5 and 6 and 7 and 10 and so on. So if I now turn on my statistics IO and I run my plan, if I run these 2 executions, I have 800,000 records. It's okay. I have 2 plans. I have a parallel plan, both parallel plans. So the engine thought that is too much costly, and maybe with a parallel plan it will be faster, which is true because it used the parallel plan. However, see here that the total execution time is a difference between 304 milliseconds and 58 milliseconds. And we are reading 800,000 records from the table. Even here, we are taking already 291 milliseconds compared with 56 milliseconds. What happens? So what happens, once again, is that due to my poor data type definition, or my variable, I'm doing more scans and more logical reads on the table compared with the one that has the proper data type. So I'm doing more or less 100,000 more IO and reading 7 more, or need to touch at least 7 more partitions. And we can see that also, well, in this case, we see here that I have a date time for the first one and a date for the second one. And the thing is that these dates can be converted on the fly to the data type that I have before, which is for my table, the date time, what it is, the date time 20. So this is a precision that goes until to the second, okay? And with the time, we also have the time portion of it. And therefore the engine says, well, I cannot safely ignore the other partitions because the data types doesn't match. Let's go and double check this. Yeah, and here showing that in the end, what you should be doing is running the datetime 2, because that is actually the data type that you have on your column. And when we do that, we can see here that I just touch two partitions. And whenever we do the other way around with the datetime, we get 12 partitions. Okay, questions here? So how we are on time? We still have 40 minutes, or
Yeah, you still have time.
Okay. I just want to go too fast. All right. So we have seen a couple of different examples, and the one that I want to show now is it's an important one to keep in mind when creating your tables, because one of the reasons and one of the main the time when you need to be aware of data types that you are using is while building your tables. Why that? Because if you go too greedy or if you go with huge data types, it can hurt performance again later on, or even with a few records, you can start having some problems. Let's see an example. I have created already a table and inserted a 10 million records on that table. So the table has an ID, which is a big int and is a identity value. So it will increment from 1 plus 1 plus 1 and so on, which being a big int, it occupies 8 bytes on our record. I will have a unique identifier that I'm putting here as being NVARCHAR 50, meaning if I occupy the 50 characters at max, it will occupy 100 bytes on my record. And I also have a date of birth that I'm using as a date time, and the date time is also 8 bytes. So if we do a quick math, on average, each record, just for the values, just for the data, it will have 8 plus 32, and I will explain the 32 in a second, plus 8 bytes, meaning that each record will occupy 88 bytes. Come on, storage is cheap, 88 bytes, who cares? What is the problem here? On the UUID, let me show you why I average to 72. Because if it is a grid, the unique identifier, a grid in the end has these amount of blocks of 4 characters, which in the end will be the 32 plus the 4. So we have all these blocks, and then we have 4 dashes, and altogether as a string, this means that we have 36 characters. However, because our data type is a Unicode and NVARCHAR, the 36 will convert in 72. Okay. So I have inserted the 10 million, so I can show that I have if I'm on the right database, I can show you here that I have some data inside. And what is the table size after all, after these 10 million records? So if we check just the data, we have around 1 gigabyte. 1 gigabyte for 10 million records on this table. But now let's say that I'm not that greedy and I can fine-tuning a little bit my data types. And I will have called less excessive data types that when I have an ID, I'm not being a big int, but an int, again, your mileage may vary, but here for the example, I think this is a good way to see it, meaning that if it is an integer, only occupies 4 bytes. Our UUID, because I know that this string doesn't have any special characters, so any alphabets, different alphabets, I don't want to have this extra byte per character to save that. I can convert it to a non-Unicode, and I can say that it will be 36. To be fair, I could even say it's a char 36, so always occupy the 36 characters. And for my date of birth, I said, well, I don't think that having milliseconds and stuff on my day of birth is needed. So since 2008, if I'm not wrong, we have datetime 2 data type, which we can have here a different precision. And by being 0, which is the smallest one that you can have, it will be year, month, day, hour, minute, and seconds, and that occupies only 6 bytes. So in the end, if we sum everything, we have now 46 bytes instead of 88 for the values on each record, okay? I have already inserted also this data, which is here. As you can see here, we have just hour, minute, and second, not the milliseconds like we had before with the date time data type. But most importantly, in this case, for the demo, what is the data types or what is the size of this table? So we can see here that we went down from 1 gigabyte to 583 megabytes. So just by adjusting a couple of data types, and I'm not, you saw that I'm not even using NVARCHAR max and stuff like that, but here just to show that using this way, we are lowering down our table by 30-something% just by using a proper data type or a better data type and not being too greedy with huge values. But there is one other tuning, let's say, that we can do in this case, and for this example, which is, yes, I still use the int for the ID. I don't want to go just to small int because that will be very few records for my table. So still 4 bytes. But now, as I'm using, and I know that is a unique identifier, why not using the unique identifier data type, which occupies 16 bytes? So instead of having the 36 bytes from the non-Unicode text string, I can have 16 bytes. And also, since 2008, we had a split between the date time, having a date and a time field. So normally, the day of birth, we want to know the day, but not the time. So why not just save the dates and therefore occupying just 3 bytes in this case? So summing all together, we go to 23 bytes instead of 46. So another 23 bytes below. I also have inserted this data. And here you can see that we don't get the time portion of it, which is okay. It's the date of birth. We want to know a day and a month and a year, but not the time itself. Our unique identifier is still this unique identifier, and our ID, our integer that we defined. What is the space here? 310 megabytes, more or less. So from the beginning of our example, where we kind of didn't care or didn't have much attention of the data types that we want to use, we went down like 60+% on the size just by having 10 million records on one table. And we are just talking about 3 columns, okay? Because you can think about these with less records, but more columns, okay? Normally when someone says, oh, this query is slow because this table is too big. When I say what is too big, people say, oh, 10 million records. That says nothing to me. For me, it's important the size because I can have much less records, but more wide the table with more columns. And depending on the query that is run, that makes a difference. Just to give a example for this situation with the data types, I work with a client that had a table with 2 columns, an ID, which was a big int, and a unique identifier, which was NVARCHAR 50. They had 14 billion records on that table. And you say, well, what is the problem of that? Well, none, unless that they had more than 2 terabytes on that table just for that 2 columns. So again, these depends, but the main question in that case was that we did some housekeeping and we lowered down the table to like 40 gigabytes because the table was not being housekeeped. But still, what we found was a column name called UUID, which, okay, it's a unique identifier. You select a couple of records, you see unique identifiers, but the data type was text. So it was wasting like 20 bytes per record just to save the 36 bytes and characters instead of having a unique identifier data type. In that case, we didn't change the data type and so on. We just warned the client that doesn't make sense and maybe they will need to think about it. They said that maybe in the past they could have a shorter value, so it was not always a unique identifier. So yeah, again, bad decisions, a table that is a one size fits all, and then you have these problems. But yeah, we could save a lot of storage to the client. Also, the refresh process between environments became faster. They reduced costs on backups and actual running data. They had the availability group, so think that twice, right, times two. So all these things together doesn't seem very important, but whenever you put everything on top of it, you can end with a big bill, with a big a bigger problem in the end. All right, so let's see side by side these ones. As shown before, the main difference visually is that we lost the millisecond part here, and we lost all the time here. Other than that, everything seems like the same. However, we know that isn't the same behind the scenes. And when we compare the three here, we see the 1 gigabyte, 580 megabytes, and 310 more or less megabytes, just by having the same number of records, but with the different data sizes and data types on the columns. What I want to show you also is what happens, because we are until now we were just looking to a table with some primary key with a cluster index. But then if the table is too big, the odds that we need some non-cluster index to help filtering data and to get data faster for specific situations, that will increase. So let's create here some non-cluster indexes. And if we check now the data here, look that now our index size that before was just a couple of data page. So each 8 KB here will be a page, okay? On the index size, the 3 version of the index until we get to the leaf level is also counted here in the index size. But we had very few, so let's say 4 megabytes max or something like that. And now we created an index on our UUID column, because here is a NVARCHAR 50 occupies 200 megabytes, here 100 and something megabytes, and here again 130 megabytes. If on top of that, sorry, this was on the date of birth. If on top of that we pick, let me just grab these values so we can compare. If on top of that we create an extra index because we also want to filter by a specific UUID, let's see what happens. Think about the time that the index can take to create, because it needs to read the table to create the index. If the data types are bigger or occupy bigger, you need more space in memory. You can see here that it needs to read this amount of page, and took 12 seconds. The second one read like almost like 60% or so, and took just 9 seconds, and the last one took just 6 seconds and read much lesser than the other one, okay? And if we check the space again, and if we go here to compare, we went from 200 megabytes to 1.3 gigabytes. So now with 2 indexes, because we have just 3 columns, and because the primary key, the cluster index, is part of the non-cluster still, we have more space in indexes than the actual data, which is 1 gigabyte. The same thing here, 600 megabytes, and the same thing here, 387 megabytes. But see the difference and the ratio between those when we lower the data type and the size of those data types to a more correct one in the end for the things that we have. As I said, this is just for a table with 3 columns. Imagine wider tables or bigger amount of records, the number of records being much bigger. And also a very important thing, if you had like some Unicode or non-Unicode max columns, you cannot index those columns. So whenever people say, oh, but I don't see any difference, why not having every single column as being a varchar max or an varchar max? And you can do that by default. If you don't have the data type, you cannot infer. If you have a string, you won't lose precision or don't lose that data type. However, think about doing applications on top of it, on doing filtering, on assuming that, as we saw before, that a column called codes is a number, but after all is a string, and you want to order by that one, and so on and so on. So be aware of that, and lob data types like the NVARCHAR max cannot be indexed with non-clustered indexes. Therefore, that is also can be problematic. And I can tell you, it's much, much easier to have a proper data type in the beginning of the process, rather picking a table with billions of records, and you want to change the data type of that record so you can be able to index that column and so on. Okay.
We have a question coming in.
Okay.
From Fernando. So he's asking if you have a data type with suffix max, will it save each record on a single page?
No, that doesn't happen. So the NVARCHAR or VARCHAR max can hold up to 2 gigabytes of data. However, what happens when you save the data and you have NVARCHAR max, but you say, oh, it's just 100 characters. If that fits inside of the record and inside of the 8 KB page, which will fit in this case, in this example, you want to have these the data offloads to the other allocation units. So because the data type exists, you will see that you have the lob data and the row overflow data, okay? But until you get to a size that you cannot fit the record any longer on that page, it won't overload or won't put it on each single page. So it will be multiple page, but they are on a different address memory. In this case, the max is also used as a lob data type, a large object data type. Right. Last example. And in this case, my favorite one, because again, only until you get to a certain point with the systems that you need to work, you won't probably see these problems. But then when they appear, it's nice to understand what's happening and why it's happening. And let's keep on the same tables that we had before. Let's assume that we had this database, and let's see what happens when we start heading on these bigger tables, and we want to, or we need to have some kind of memory grant. So first of all, a memory grant is a memory that SQL Server needs to start a query. And I will repeat, to start running a query. So until it can grant the memory grant value that is requested by the engine, if it cannot grant, that query will become with a specific wait type. So for the user, for you, you will see your counter on time going up 1 second, 2 seconds, 3 seconds. However, until it gets the memory grant, the execution itself won't start. Okay, so you have the session open, but you will think, well, this is much slower today. And it is, because it's waiting to have the available memory grant to start running the query. Okay. I won't go very deep on these details, but because this could be probably just a session by itself, but just as an overview, memory grants are needed when you have sort operations, when you have like hash match operators on the execution plan, because those things happen in memory, and SQL Server needs to get that memory to work. Now the question is, how much is that memory? How you kind of calculate, or you can kind of estimate which one will be needed. So first of all, just giving an example, or saying that SQL Server by default won't give 25%. This is more or less this value, okay? Because I have seen 25 to 30%, but 25% of 75% of the max memory that you have set on your SQL Server instance. What this means, it means that if I have an instance with 4 gigabytes as max memory configuration, it can use 75% of that, which is 3 gigabytes for the memory grants. And each query will be able to request up to 0.75 or 750 megabytes, again, more or less, memory to run the query, okay? Why is this important? Let me do here a quick parenthesis. If you run the standard edition, for instance, you may have seen before that there is a cap on the max memory that you can have for the buffer pool, which is 128 gigabytes. And that is correct. You can have 128 gigabytes for the buffer pool, which also contains some memory quirks and some other stuff. However, what about in memory? What about the column store indexes? Even with standard edition, you get some extra gigabytes for those things, which doesn't count inside of this max memory setting. So it's a part of that. And here, memory grant is also one that can benefit of that. Meaning, if you have a SQL Server that will have the standard edition, you may say, well, then just put in me 128 or 132 gigabytes on the box, because I will cap SQL Server to 128. I will argue that put it 172 or 192 gigabytes on the box, and you put you let like 12 gigabytes for the box, depending if it's not running anything else. I'm assuming it's just a database server. But the rest you put as a max memory, it means that your memory grants may be able to benefit from that, because as it is 75%, 25% of the 75 of this max memory, if you don't cap that on 128, but you put it on 160, you get some extra megabytes per query for the memory grant, if, of course, needed, or as we will see, it's just enough that we are running in parallel a bunch of similar queries that ask for the same memory grant, and if that amount all sum all together cannot be fit inside of these 75%, the query will start waiting to be able to get the memory grant, okay? Now, for this example, I will go here to my grid and discard the results after execution, because most of the time of the execution of this query is not execution the query itself, but rather drawing the results on the grid. And if I run this way, I won't have any results here, which would be the grid, the date of birth, and from 2 million records for each table. And if I turn on my actual execution plan, so the plan that was run after it, we will have here 3 of them. And let's have a look. So what can we see here right away? So how much time it took each query to run? Let's say it took 2.2 seconds for the first one, 1.5 to the second one, so more or less a second faster, and 1.1 for the third one, okay? Why? It's the same query with the same order by, but on top of different tables, right? That we saw before that has different data types. So here we can see that even just for scanning the data and not sorting and so on, we already have some difference, small, but still, between just the scan of the cluster index. Even the cost is different for the engine for these ones. But then it becomes more evident when we check the sort operation, because we have a order by UUID, right? And here we see that it takes longer and even longer, okay? When we mouse over our select here, we can see what is the memory grant that was requested. So for this query, it was requested around 294 megabytes. So imagine that you have your server in stress, you don't have much memory left, but you are asking to have these 200 megabytes, and SQL Server needs to make room for it. It can take some time. And what is the difference for this one? Like 90 mega less, 90 less. And what about our better better query or better table with more precise data types, less than 200 megabytes. So this is important because these sort operations that happen here will tell us something like, oh, come on. It will tell us something like, I request X memory, that X memory still was not enough, and I had to spill data, which is the writing operation to the TMTB, will be the slowest operation here. And it says how much memory was granted. You can also, from the selects, you can also see the memory grant info here, and you can see the desired in the KBs. You can see here the max query memory could be available would be the 749, so more or less the 750 that I said to you before. And it says also that it used this amount of memory, and therefore you request it to the engine. In this case, and if you are aware, there is some new features with in-memory, the memory grant feedback. In this case, just to show the point, I'm using the option recompile, so I get a new plan every time that I run, because if I do other way around, and because I'm using a developer edition, I will get the enterprise features, and after a couple of executions, the engine will say, oh, this is excessive memory grant, let's reduce the amount of memory needed, until you get to a stable point, and from that point on, it will use that one, which is a cool thing, is a cool feature. It can help you to automatically fix this memory grant issue after running a query a bunch of times. So we already saw the times. Now let's see what happens when we run this, and let's pick our excessive data types and put it here on top. And in this case, I will just say that I want to run one iteration, do one run spread on 6 threads, okay? And for this one, let's use this one here. And also one iteration spread on 6 threads. So if I run this, it will take some good amount. And while it's running, I will be using SPU is active to show what is running on the server. And now you see that we have our query running, and by now it should already finish. So it took more or less 30 seconds. If I run for my other table, which has the same data, but better data types, which we saw before that the memory grant was lower, and the data size is lower, and the size it occupies in memory will be lower. So everything builds up and everything sums up. We get less 20 seconds. Okay. So why and what's happening in this case? Let's run this again and see what's happening when I do this. You see here, let me bring 2 informations. So you see here that 3 out of my 6 sessions are waiting on something called resource semaphore. So the resource semaphore is the wait type that indicates memory pressure. In this case, indicates that SQL Server cannot grant a memory grant to the query to start running. Another way to see that is from the dmexec memory query memory grants, and you can see here that there is a grant time column. When that is fulfilled, it means that the engine gave that memory or the requested memory to that session. Whenever it's null, it's saying, I'm waiting for it. So what happened in this case is that we had 6 executions in parallel, meaning that we had the 300 or 290. Let me run again to get that number, but we had the 290 megabytes. So if we run this one again, if I get this, and if I check one of the execution plans, if I go here, I see that my memory grant should be 649 megabytes. If you do this time 3, it will give you like almost 2 gigabytes. However, there is also an overhead, as I will show, because the plan is in parallel. So there is more thing, meaning that the engine in the end with 4 gigabytes of max memory for this query cannot have more than 3 queries in parallel running, because the 4th query will make the request go above the 3 gigabytes in the end. So altogether, it could only have 3 of them running. And if we check here, this is our comparison, and now I will run like 10 threads. If I come here and get what is running, you can see that out of 10, only 1 is waiting for the memory grant to be able to run, meaning that after all, I can have like 3 times more the same query running in parallel on the same system. Does it make sense? Can I have some thumbs up? Thank you. All right, we can also see here on our memory clerks, let me make it run again so we can see the situation. So we see here, memory clerks is how things are divided and being occupying memory, and we can see our SQL buffer pool where our data resides is occupying 1.8 gigabytes, and the memory clerk SQL reservations, this is for the memory grant. And we can see that just the 3 that are running is doing 2.5, right? Well, with whatever else SQL Server is running behind the scenes. But the thing is, if you divide this by 3 and you have a 4th query, again, you know that this will be above the 3 gigabytes, which is the 75%, meaning you cannot run, okay? And you can also check how using the MOS buffer descriptors, you can check like which data page you have in your buffer pool. So you can see our previous tables on previous examples, but then we can see here our less excessive, how much the cluster is doing, the better data size, and so on and so on. So this also gives you an idea what is occupying the space memory in the query at this point. So we saw the wait type. We saw that you can use SQL is active to monitoring or to get that. Now here, let me show you what I said before regarding the memory grant and the parallelism. So in this case, what I'm saying here is I'm running the normal query because of the cost of the query and the cost for threshold parallelism that I have. The engine says, let's try a parallel plan. And that gives these 289 megabytes. But if I go here and I force the query to run with the max stop 1, meaning just a single thread, you can see that the memory grant just goes down by some megabytes. So this is the thing about you need also memory to keep the data on the sort and to pass it to the gather strings and so on. So there is an overhead with that. So now let me turn off the discard results. So we want to have the results again. And I want to show you high level how the memory grant can be calculated or is calculated by the engine. This is not 100% accurate to the byte or the kilobyte, but the point is for you to understand how that works. So let's say that I have a memory grant table with an identity column into a number which is an integer, and then I have 3 columns, and each one are from the varchar data type. But One of them has a max of 500 characters, the other one 4,000, and one has the max. And now I'm fulfilling this table, the memory grant, with top 3,000 for my syscolumns, and I'm fulfilling a column ID for the number, the name on the other 2 columns, and I'm having a null for the description of the max. Okay, so the max doesn't have values like you see here, but is still on the table, is a column, and so on. So what can we see here? So if we skip this first one, which is the insert, let's see these 3, actually 4 queries. So if I see the first one, which is the description 500, I can see that SQL Server decides to request 1.2 megabytes, more or less, for a memory grant, because I'm doing some order by, and it's doing this 1.2 megabytes. If I'm asking for the description 4,000, now I no longer have 1 megabyte, but I have 5.5 megabytes, okay? And if I'm using or asking for the max, which is empty, by the way, it has null, not empty, is null, because null has no value there. Empty will be a empty value, but is null, doesn't have anything. But still, it says, well, give me 7.5 megabytes to run these things. And finally, if I say on this final query, which is give me everything ordered by the number, which is the entire table in the end, 11 megabytes. Okay. So how this happens? It happens because SQL Server will have an idea what is the average record size based on the data types that you have. And for the variable data types, so the ones that can are not fixed and can be between 1 or 500, it will always assume 50% of that. So it will always assume around 250 for this one bytes and around 2,000 bytes for this one. And for this one, it will get 4,000 because the varchar max before being the max is the 8,000. So it also assumes to be half of that. So if you don't take this in attention, whenever you run these things, you can get the problem that we saw before of the memory grants piling up and having a resource semaphore wait type, and you think that your queries are running, and actually they are not, because they are waiting for the memory to be able to go on. Okay. Any questions?
Well, we just had a question coming in from Hans, who is asking, what is your take on choosing between varchar and NVARCHAR? When it is very unsure to ever need a Unicode character? I mostly see NVARCHAR as defaults in database designs.
Yeah, okay. Yeah, that actually depends on your business or whatever you are taking and saving on the database. If you have let's call it a worldwide application and you need to have to sell and to have the possibility to save like Cyrillic alphabet or like Chinese alphabet, Japanese, and so on, you will need to have NVARCHAR. Otherwise, you cannot save those characters. Okay. However, if you are more within the European Union, let's say, and America, probably you won't need that, because even my name that has the accent on the A, you can have a varchar and it will work. So it really depends on what you want to save and to from your customers and to show to your customers afterwards. And also be aware that you can have a mix between non-Unicode and Unicode on the same table. So if you really have just one column that makes sense to have the Unicode, sure, go for Unicode to that one and don't go for the others if you don't need them, because otherwise you have this overhead of the double of the bytes, and that will be, can be problematic in the end on, as we saw today with table the type of variable that you declare, the size in memory, the refresh process, your backup size, your storage, and so on and so on. Hopefully that answers your question. Well, thanks, Hans. Yeah, so these were the demos I had for today. I hope that you have enjoyed. If you can then provide feedback on the meetup or something, that will be nice to understand if you feel that you missed something, or or I missed something. Let me just drop in the chat the URL for my GitHub, where you can get these T-SQL demos, and from that point you can play by yourself and change whatever you need to change and so on, to see the things in action. Just be aware that the different environments with the different settings and so on can lead to different situations, and you may be seeing a problem, and after a couple of executions you no longer see the problem. Example, the memory grant feedback that I mentioned before is one of those situations. So it's important and cool that we have these features and these improvements, but it's also important to understand that not every system is running like enterprise, and if you know the problems, you know how to analyze them, and then you can filter on top of that with if it is enterprise or not, and so on. But at least you know what is the symptom behind it. Cool. Thanks, Sam, for the feedback. I dropped the link that goes directly to the PDF, and inside you have the data types. The data types folder with the setup and all the other things. Oh, and by the way, I don't know if the person that asked about the anti-patterns is still here. There is this article when I saw it first a long time ago, June of 2023, from Dennis Torres, that shows you one of those examples that I was saying. So long inquiries, some and or filters, and also the implicit conversion ones, at least. Oh.
Okay. Thank you, Claudio.